Greetings, dear listeners. My name is Serikbayev Syrym, and today our broadcast is dedicated to soft robotics. Soft robotics is a subfield of robotics that concerns the design, control, and fabrication of robots composed of compliant materials instead of rigid links. In contrast to rigid-bodied robots built from metals, ceramics, and hard plastics, the compliance of soft robots can improve their safety when working in close contact with humans. Types and designs. The goal of soft robotics is the design and construction of robots with physically flexible bodies and electronics. Sometimes softness is limited to part of the machine. For example, rigid-bodied robotic arms can employ soft end effectors to gently grab and manipulate delicate or irregularly shaped objects. Most rigid-bodied mobile robots also strategically employ soft components such as foot pads to absorb shock or springly joints to store release elastic energy. However, the field of soft robotics generally leans toward machines that are predominantly or entirely soft. Robots with entirely soft bodies have tremendous potential. For one, their flexibility allows them to squeeze into places rigid bodies cannot, which could prove useful in disaster relief scenarios. Soft robots are also safer for human interaction and for internal deployment inside a human body. Nature is often a source of inspiration for soft robot design, given that animals themselves are mostly composed of soft components and they appear to exploit their softness for efficient movement in complex environments almost everywhere on Earth. Thus, the soft robots are often designed to look like familiar creatures, especially entirely soft organisms like octopuses. However, it is extremely difficult to manually design and control soft robots given their low mechanical impedance. The very thing that makes soft robots beneficial, their flexibility and compliance, make them difficult to control. The mathematics developed over the past centuries for designing rigid bodies generally fail to extend to soft robots. Thus, soft robots are commonly designed in part with the help of automated design tools such as evolutionary algorithms, which enable a soft robot's shape, material properties, and controller to all be simultaneously and automatically designed and optimized together for a given task. Uses and applications. Surgical assistance. Soft robots can be implemented in the medical profession, specifically for invasive surgery. Soft robots can be made to assist surgeries due to their shape-changing properties. Shape change is important as a soft robot could navigate around different structures in the human body by adjusting its form. This could be accomplished through the use of fluidic actuation. Exosuits. Soft robots may also be used for the creation of flexible exosuits for rehabilitation of patients, assisting the elderly, or simply enhancing the user's strength. A team from Harvard created an exosuit using these materials in order to give the advantages of the additional strength provided by an exosuit without the disadvantages that come with how rigid materials restrict a person's natural movement. The exosuits are metal frameworks fitted with motorized muscles to multiply the wearer's strength. Also called exoskeletons, the robotic suit's metal framework somewhat mirrors the wearer's internal skeletal structure. The suit makes lifted objects feel much lighter and sometimes even weightless, reducing injuries and improving compliance. Collaborative robots. Traditionally, manufacturing robots have been isolated from human workers due to safety concerns. As a rigid robot, colliding with a human could easily lead to injury due to the fast-paced motion of the robot. However, soft robots could work along humans safely, as in a collision to compliant nature of the robot would prevent or minimize any potential injury. And now our broadcast is over. Please subscribe to this channel. That was your host Serikbayev Syrym. Goodbye.